online open source voting basics, hashes, timestamps, and digital signatures. In this video we will briefly go over some basic concepts from cryptography such as digital signatures and hashes that are important to understand before discussing how you construct a secure online voting protocol. For more information on these topics, we plan on putting out an introduction to cryptography video sometime in the future. The first thing we will talk about are software fingerprints, known in the industry as hashes. A document is run through an algorithm called a hash function to produce a digital fingerprint. For example, the common algorithm SHA-256 produces a 256-bit number from the document. There are 2 to the 256th power or 1.2 times 10 to the 77th power possible combinations of this 32-byte number. To put the number of potential combinations in perspective, scientists believe the universe to be 4 times 10 to the 17th power seconds old. The number of atoms in the Earth is approximately 10 to the 50th power. If you multiply the number of atoms in the Earth times the number of seconds since the beginning of the universe, that number would still be about 10 orders of magnitude lower than the odds two documents having the same fingerprint. A collision is when any two documents have the same fingerprint. Therefore, the chances of such a collision are astronomically low. It is close to mathematically impossible to prospectively produce a document with specific fingerprint, and there are algorithms like SHA-512 that generate 64-byte hashes with 10 to the 154th different combinations that make a collision even more astronomically unlikely. Bitcoin electronic mining is based on this problem. People who mine Bitcoin will try all sorts of random digits to produce a very small portion of a fingerprint from a hash function. The one who finds it first gets free Bitcoin, which is sort of like winning the lottery. So, for all intents and purposes, if a fingerprint matches, then you can basically assume the documents that produce the fingerprint are the same. If a software publisher publishes a 256-bit signature of its code at its website, then if you have a copy and run it through the SHA-256 algorithm and it is the same, you can assume that you have the right software and not a version that has been modified by a hacker. Comparing these digital fingerprints of authentic software to the hashes generated by the software on your system is one of the primary ways you can prospectively look for malicious code on your computer. Let's look at how this works in real life. On this page you can click on Main to download the Ubuntu Focal 64 version of the Puppy Linux operating system. After downloading the software, you click on the underlined checksum link. That will take you to this page where you can see the fingerprint, or hashed checksum, of the software 6A45E7A305B7D3172IB9E5CA460E4 as well as the name of the file we are supposed to be downloading. This appears to be one of the weaker hash algorithms MD5 that only generates a 128-bit hash. Now if you are using Mac OS, you can open up a Mac terminal and type in MD5 and then a space and drag the file over to the terminal to produce this. You press enter and wait for a little bit to produce the hash. As you can see, we get the exact same fingerprint value back, which means we have the proper software and there were no data transmission errors and we have the correct file. Hashes also are how passwords are usually handled on servers. Computer servers store hashes of the password, and not the password itself. When you log in, the computer will take your password, hash it to get the fingerprint and then compare it to the hash in the database for your username. If it matches, you are logged in. Hashes are one-way functions. You cannot produce a document or a password from a hash unless you have a limited number of possibilities you can randomly check. So, an administrator cannot just get a person's password from looking at the stored hash of a password. That is why the password information is stored this way. There are databases of common passwords and their related hashes that hackers use to try to find passwords to log in from a list of hashes they might have stolen. For this reason, random data or assault is added to any password to create a unique hash that is not on these hacker tables. Hashes are almost always used with digital signatures, which we will discuss next. In general, if we say a document is digitally signed, then what we really mean in most cases is that the document's hash was digitally signed. The only exception would be for documents that consist of a really small file such as a voter identification number. Then that number can be signed directly without using a hash function on it first. Digital signatures are electronic equivalents to physical signatures, except they are more secure. It is easier to forge a physical signature than to get access to a quantum computer that can break a digital one. Think of digitally signing an electronic document as applying a password you only know to the document to approve you agree with it. With a digital signature, the password never needs to be disclosed for someone to verify you supplied the right password. If you remember the discussion earlier, when you enter in your password to a computer, it takes your password and then hashes it to see if it matches the fingerprints in the database. However, if there is malicious code on the computer, then it can capture your password after you enter it and send it to a hacker. This is one reason you should always use a different password for every website you log into. Now, it is unlikely that a computer you log into will be looking to steal your password data, since they have access to all of your data already. But if you had a password that was used for authorizing everything, then the server administrator might be much more likely to keep that password data. With digital signatures, you never actually need to disclose your private code that is used to authenticate a document. This is accomplished through mathematics using public key cryptography. For more information on digital signatures, see the Introduction to Cryptography video we will be putting up on our site. Basically, the password is the private key that only you have. And public key cryptography element corresponding to a login username is the public key that is mathematically related to the private key. If you sign a digital document like a vote with your password, your private key, then it attests that the person identified by the username, your public key, approves it. This works because public key cryptography is asymmetric. There are different keys that are used to encrypt and decrypt a document. If you encrypt a document with your private key, then it cannot be decrypted with your private key. It can be decrypted with your public key. Conversely, if you encrypt data with your public key, it cannot be decrypted with your public key, only your private key can decrypt it. Typically, you do not use public key cryptography on an entire document. That is because it is a very computationally expensive process, using numbers that are 1028, 2048, or 4096 bits long when the microprocessor is only designed to efficiently process 64-bit integers. So, what you usually do is use a hash function to generate a 256-bit fingerprint of the document. That fingerprint is then encrypted with your private key to produce a digital signature for the entire document. To verify the document is approved by you, a computer will decrypt your signature using your public key. That will produce the original fingerprint. The computer will then hash the document to generate the fingerprint. If the hash of the document matches your decrypted fingerprint, then they can assume that you generated the signature with your private key and the signature is valid. If the signature is invalid, the decrypted signature will not match the document fingerprint. Many times, software manufacturers will digitally sign their software using such a method. They will have their public key available on a public key server for people to validate. They then encrypt the hash of the software, like the hash that was published at the Puppy Linux site. This is encrypted with their private key. Anyone can then download the software, and take a hash of it. They can then download a digital signature associated with the software and use the software company's public key to decrypt it, and it should match the hash of the software you just downloaded. Many operating systems such as Mac OS and many Linux distributions will use digital signatures to confirm that authentic software is being installed on your computer when you install the software properly. We will be using digital signatures to verify documents that represent votes of the voter in a system we will outline. Digital signatures will also be used to verify the authenticity of other public keys. This is done by having a high-authority private key signing the hash of a public key of an employee or other authorized representative. Private keys for digital signatures are generally stored on a hard disk and encrypted with a password that you create. That way you have to have physical access to the hard disk or thumb drive the private key is on and the password to unlock it. At least that is how private keys should be managed. If you keep your private key on a thumb drive, or more than one thumb drive as backups, then you can hide it somewhere. It is generally a lot less vulnerable to online attacks than if you keep it on your computer all the time. But these digital signatures will serve to verify both your vote and your right to vote in this voting protocol. Another common use of public key cryptography is the transfer of information over the internet. If you are having an electronic conversation with someone you have never met before, you cannot exactly exchange a conventional symmetric key in the open to encrypt data. People could intercept it and decrypt everything you said. So, what is done is computers will take that symmetric key they would have sent in the open and encrypt it with a public key of the person or server they are sending the message to. The computer on the other side will use its private key to decrypt the symmetric key and thus the rest of the message. Since only the receiving computer has access to its private key, it is the only one that can decrypt the data. This is basically how all secure communications on the internet works. One final note on public key cryptography and digital signatures. If a state-level actor has a working quantum computer, these are highly vulnerable. Using Shor's algorithm, quantum computers can break public key cryptography quite handily. This technology can break every secure message sent via Secure Socket Layer (SSL) encryption such as online payments. The good news is now this technology is very expensive and is generally going to be used by state-level actors like the US National Security Agency and some of their private contractors. Hashes and symmetric cryptography can be made more vulnerable with quantum computers, but they are not nearly as easy to break. We will discuss mitigation of the threat from quantum computers in another video. Finally, we will discuss timestamps. Timestamp servers are ways to validate that a given document was produced before a certain time. Basically, you send a document to the server. The server checks its internal clock and adds that to the document to produce a new document in a very specific manner. A fingerprint or hash of that document is taken. The time server then uses its own private key to digitally sign the hash of document with a timestamp and then sends the document and the signature of the document back. Assuming the person managing the timestamp server can be trusted, this is valid evidence that the document was produced at or before the date stamped. This is how you prevent unscrupulous people from backdating documents. To do so, they would have to either get their own quantum computer to solve the private key of the timestamp server or bribe the person who owns the timestamp server to backdate the document. If you want more redundancy, you can send the document to multiple time servers to make colluding with the time server administrator harder. If you want to timestamp private information such as votes and vote identification numbers, do not send the information to the time server, you send an encrypted version so private information is not disclosed to the owners of the timestamp server. The encryption key can be hashed and appended to the encrypted document sent to the time server. You cannot recover the encryption key from the hash to decrypt the document, but someone with permission to view it will have the encryption code, and can prove it is the one supposed to work on the timestamp both from the hash of it and the fact that it will successfully decrypt the document. If we mention timestamping something with private data, assume that this process is done first before getting the timestamp. With digital signatures, hashes, and timestamps, you can create an auditable trail of every step throughout the voting process.